6.3. We're going to talk about some exponential functions. In order to do that, I've got to define a number for you. We're going to define what the base of a natural logarithm is. I think you've probably seen this before. E. You ever heard of the number E before?
Yeah.
Number E is an awesome number. This guy way back in the old days, name was Leonard Euler. I know, awesome name. Discovered this number. It's an irrational number. It goes forever, very much like pi. 2.7 blah 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 blah. Forever and ever and ever. It's not rational. Occurs so much that this guy said, you know what, this is crazy. This number is found in nature all the time. We use it for engineering all the time. This number E, we're going to call it the Euler number, because in German, Euler is not spelled O-I-L-E-R, it's spelled E-U-L-E-R. So the E comes from Euler, but it's spelled different than we usually spell it. So anyway, it's called the Euler number or the natural number. And how we define it, E is defined as this. It's a number that, when I say ln of this number, it gives me 1. So, I'll give you another definition too. It's kind of a more mathematical one. It says, hey, you know what? If I had, do you remember this?
Yeah.
That was true, because we developed that basically in kind of the first day of class. We did that. We said ln x is equal to the integral from 1 to x of 1 over t dt. Well, what that implies is that if x now becomes e, ln x, well, ln e. 1 to x, well, 1 to e. This has to equal 1. Sorry, forgot my equals. If ln e equals 1, that's our definition here, folks. That means that this integral also has to equal 1. Do you guys remember that the integral is the area under a curve between 2 points? That's what a definite integral is. So what this says is the area under this curve is 1. So another way we can find it. By the way, if you're curious as to whether this number actually exists, by the intermediate value theorem, it has to exist. By the IVT, because, so a little bit of a side note here. Because natural log function is continuous everywhere, if I could spell it right, and the range is negative infinity to positive infinity. What the intermediate value theorem says is this: if a function is continuous along its range, then for any number along the range, you can find an input that verifies that output. So basically it says, because natural log looks like this, the range goes from negative infinity to positive infinity. Do you remember this graph here? It's that one. Because it goes from negative infinity to positive infinity, that means that any output that I choose has to have some sort of an input. That's what intermediate value theorem says. Well, because natural log is continuous everywhere, and because the range is negative infinity to infinity, that means that there has to be some input that when I plug it in, it gives me 1. There has to be. Does that make sense to you? There's got to be. It goes from negative infinity to infinity. Every single point is continuous. It's continuous. There's no holes or gaps. That means that I've got to be able to plug something in to get a 1. We call that number e. That's how it's defined. Does that make sense to you? Okay, so the number e has to exist. It's got to be part of the function. last definition that we got for this. So we define it. If ln of y equals x, we have that if and only if e to the x equals y. That's how we go back and forth between exponentials and logarithmic notation. If you don't remember that, what's the base of ln? It says base to the power gives you the argument of log. That's what we have right here. Now what's kind of cool about this is we got a couple properties that are going to help us solve equations that have e or ln in them. So I'm going to go over those properties with you right here. We're going to do a few examples. So first property. First one is kind of so nice. The first one is this. If you have ln of e to the x, so ln of e to the x, do you know what the answer is going to be?
X ln.
Okay, you can move the x in front of the ln. Do you remember doing that?
Yeah.
Okay, but this is also cool. How much is ln of e?
1.
That was our definition. So what this is equal to is x.
Oh.
The reason why is because if you want the proof, here's the proof right next to it. If you bring this down, we have x ln e, how much ln of e?
1.
Equals x. There's the proof for that. Number 2, the other one. If we have e to the ln x, do you know how much that's equal to?
E.
It's equal to x. It's also equal to x for a very similar reason. So this also equals x. I can actually prove it to you if you really want me to. Here's the proof. If you have e to the ln x equals x, check it out. If you didn't know that these were equal, we can prove that they're equal by getting down to the same thing on both sides. So take ln of both sides. If you do, we would get ln e to the ln x equals ln x. Are you guys with me on that? Taking ln on both sides. What can I do with this?
Put it down 1.
So ln x times ln e equals ln x.
Divide by ln.
Don't even bother. What do we have here?
ln e is 1.
This is equal to 1. It proves that those two sides are equal, therefore these two sides are equal, therefore this is a true statement. Are you guys okay with those ones? Practically it's this. Whenever you have e next to ln, here or here, you can say they cancel each other, they eliminate each other. In other words, we're going to get whatever the argument is. Whatever x is, that's going to be our answer. Show of hands if you feel okay with those ones. What this allows you to do is solve some exponential or logarithmic equations really nicely. We're going to practice just a few of them right now and talk about how this stuff works for us. So we're taking a little break from calculus, I suppose. We're going to start just do some algebra to make sure you guys are good with this stuff. Okay, so it's an equation. We should be able to solve it in this class. So we got e to the 4 minus 5x equals 9. We go, oh my gosh, how in the world are we going to solve that thing? What do you think? Yeah, we can do anything we want to on both sides, as long as we do it to both sides of our equation. We can take both sides to and make it a power of e. We can take both sides and put an ln in front of it, as long as you do it to both sides. What I can't have you do is do ln here and forget to do ln here. That's kind of a rookie mistake that a lot of people make. But don't forget that you can actually take ln of both sides. So if we do that, we do ln of e to the 4 minus 5x. We do ln of 9. Someone out there explain to me why in the world we just did that. We do have to do it to both sides, but why did we bother with ln? Good, very good. You can do this one of two ways. You can bring the exponent down if you want to. You can just understand that because of this property, this is proved, right? If something's proved, you get to use it. So this says that our answer is going to be this argument, this exponent right here. So yeah, you can bring it down, make sure it's in parentheses, okay? Don't forget those freaking parentheses. You can bring it down, you go, oh, that's 1. Multiplied by 1, you get 4 minus 5x. Or in other words, look here, look here. This is 4 minus 5x. It's magic. No, it's not magic. We proved it, right? It has to work. Proved it. Equals ln 9. Don't forget about the L on the right-hand side. Quick head nod if you're okay with that one. We're moving kind of quick here because this is algebra. I just want to refresh your memories. Now what do we do?
Solve for x.
Yeah, just solve it. So we're going to...
Take the ln. Oh, no, wait, no, I'm sorry. X.
Hmm?
Subtract by what?
Cool. Subtract 4, but yeah, you're close. So I'm going to put that up front because we're going to change signs here. So negative 4 plus ln 9. Last step. What's the last step, everybody, when you're... Yeah, if we divide by negative 5, we get x equals positive 4/5 minus ln of 9 over 5. Are you guys okay with the algebra on that one?
Yeah.
So it allows us to solve some things really, really nicely that we otherwise wouldn't have been able to do. Tell you what, we'll try, I don't know, 3, 4 more together and then we'll call this good. Okay, let's go kind of almost row by row. First 2 rows, what would you do first on this step? Would you do ln on both sides right now? Good idea, bad idea? What would you do first? Yeah, in order for us to do ln on both sides, we have to have the e isolated, okay? So this 2, not so bueno. We're going to get rid of that thing. We're going to have e to the 5x minus 1 equals 2/3. Well, that's a little bit better because now we can actually take an ln on both sides. That's our next step. So whenever we get caught and we have, wow, we have some number raised to a power we can't find common bases, take an ln on both sides. Match up ln with e. We'll be able to simplify that. You just got to make sure that you don't neglect it on the right-hand side. Okay, middle people, what are we going to have on the left-hand side?
X minus 1.
Perfect. These are gone. If you're the type of person who has to cross stuff out, fine, cross it out. I don't care. You just need to know that our answer on the left-hand, or our answer, the expression on the left-hand side is 5x minus 1. Okay, other middle people, you guys, what's the next step?
Add 1. We'll solve for x.
Sure. So if we add 1, one quick thing. This is a little bit ambiguous as to what you're doing. Use parentheses appropriately here. Right now, don't add 1 to 2/3. Please don't do that. Use parentheses. That way I know you understand that it's ln of 2/3, and then after that, you're going to be adding 1. Is that clear? And then lastly, we'll divide by 5. You can separate into fractions if you really want to, or you leave it just like that. So far so good?
Yeah, that's all right.
Okay. How about this one? One more. Is this one of the ones where we want to take ln on both sides?
No.
No, that's silly. So we got ln. What undoes ln?
E.
Sure. So what do we do?
E both sides.
Make each side an exponent of e. So take e on both sides, that's fine, I don't care. So e to the ln 7x minus 1 equals, do we have to do it on the right-hand side?
You do.
It's an equation. Okay, left-hand side, what happens? E to the ln of whatever I have is, that's this one. Whenever I have this, our expression changes just to whatever the exponent is. So in our case, these are gone. We get 7x minus 1 equals e to the 9th. After that, man, piece of cake. Just solve for x. How are we going to solve for x? Perfect. So if I add 1, we get x equals e to the 9th plus 1. If I divide by 7, put the whole thing as 7, or you can write this as e to the 9th plus 1 times 1/7. Either way is appropriate, and I really don't care. Show of hands if you feel okay with how to solve these basic ones. All right, we'll practice a couple more next time, and we'll start talking about how to do derivatives with e.
The University of Arizona Online brings a top-ranked education to you. Choose from 150 plus programs, learn from the same faculty, and earn the same degree as on-campus students. Apply today and make your tomorrow amazing.
So we're going to continue talking about how to solve these equations that involve ln or e to the x. Now, one thing you'll notice on this equation, we got ln everywhere. One good idea that you have, and by the way, I'm going to go through these quickly because this doesn't really involve calculus. I just want to give you a little refresher on how to do some of these ones, things that you can and can't do. So, whenever you involve ln on both sides of your equation, one good idea would be to combine and make one ln on each side if you can. Once you do that, what's going to get rid of ln for us?
E.
Good, okay, so can we make one ln on each side?
Yeah.
How would I do that? Okay, so if I have ln plus ln, I know that I can combine those via multiplication. As soon as you have that, you have one ln on one side, and anything else on the other side, basically, as long as you have all your variables on one side and something else on the other side. Take e, put e on both sides, and treat these as exponents of e. Once we do that, and you guys already told me that you can, by the way, when I do the e thing, do I do it to one side or both sides?
Both sides.
Yeah, it is an equation. You have to do it to both sides. In this case, that's actually really nice. Because I had ln on both sides, that means that when I do e on both sides, everything's going to be gone except for my x's and my constants. So on the left-hand side, tell me what happens when I have e next to ln. Pretty much in any scenario, what happens? Okay, what am I going to have left on the left-hand side?
X parentheses x minus 1.
Perfect. Right-hand side.
2.
Fantastic. Can we keep going?
Yeah,
Yeah, this becomes a pretty easy, pretty straightforward at least, algebra problem. Let's go ahead and solve for x. We will do what?
Pass each to the other side.
Anytime you see an x squared,
Difference of square root is.
you're gonna try to factor it somehow. If you can't factor it, what would you use? Sure. So there's really three ways, right? There's factoring, which is the quickest if you know how to factor really well. Then there's completing the square. We rarely do that really because we can go straight to quadratic formula. So here we'd have x squared minus x. We'd subtract the 2. Can you factor that one?
Yeah.
As I've been rambling, hopefully you've been factoring.
Minus
Yeah. Minus 2.
2.
Which means that if we have this, we set each of these equal to 0 by the zero product property, and we get x equals positive 2 and x equals negative 1. Quick show of hands if you're okay with both our solutions. Are you sure?
Yeah.
You sure you're sure? You better look back at your problem here real quick, folks, because we need to know something about the domain of the natural log function.
Yeah, you can't have a negative or 0.
X has to be bigger than 0, that's right, x has to be positive. So, are both of these valid solutions?
No.
No. Which one's wrong?
The negative 1.
So we actually only have one real solution here. Whenever you find your answers for ln, please check them. Make sure you go back to your original, not here, not here, but here, your original. Plug it in, make sure that you don't have anything that falls outside the domain, otherwise we have an issue there. Quick head nod if you're okay with that one. Okay, let's do one more. Switch up a little bit, we'll try something like this. You know, you had something similar to this in probably your pre-calculus class or maybe in advanced algebra or whatever. Whenever we have a scenario where we have a trinomial, what's really nice is if we can fit this into some sort of a quadratic. We want to try to fit this into a quadratic. Can you fit this into a quadratic form? Here's how you know. You look at your middle term, you look at your first term. If you can take the variable part of your middle term and it's the same as, sorry, if this is the same as your middle term squared, then you can make a substitution and make it a quadratic. For instance, if I were to rewrite this, and I said, well, wait a minute, let's look here and here. Can I write this as e to the x squared? Is that the same thing?
Yeah.
This is not the same as this? Or this is the same as this?
Same.
No, it's not.
Okay. Do you remember your exponent rules?
It is the same.
Okay, let's practice some exponent. Let's practice some exponent rules. 7 or 12?
12.
Let's all try this and get it right this time. 7 or 12?
12.
Oh dear Lord. How about this one? 7 or 12?
7.
Oh, thank God. Okay. Woo. 7. Okay, good. Is this the same?
Yes.
Yes, because you multiply. What's x times 2? X times 2 is 2x. Are you clear on this one? Are you sure? Okay. I'm glad we went over this, huh? Wow, goodness. Minus 5. Let's keep this in parentheses here real quick. Here's what you try to do if you don't know immediately how to solve this problem, because I'm guessing you look at that and go, I don't know. Well, if it's got 3 terms in it, maybe try to make it into a quadratic. What I saw right off the bat is that this is this part squared. Do you see what I'm talking about? This is this part squared. If that's the case, notice how we have exactly the same thing here and here. Are you guys with me on that? Exactly the same thing. Whenever you have that, one part's being squared, one part's not being squared, you can use a substitution, just create a dummy variable like y. If you do a substitution, like y equals e to the x, then instead of writing e to the x everywhere, what could we write everywhere? Because I asked you. Just joking. Some people got this. Stand up next time, you'll get it. Whatever. That was funny. You missed it. I'm not going to edit that out. Watch it again, and you'll laugh. I promise. Okay. So instead of e to the x, we got y squared minus 5y plus 6 equals. Do you see why that helps us? Why does that help us?
Because it's easy.
Say what now? Why does it help us?
Easy to factor quadratic formula.
You can actually factor, yeah, you can factor, quadratic, whatever you want. So this allows us to actually do some things with it where this one didn't. So once you get down to here, man, this should be a piece of cake. Can you guys factor this?
X minus 3, X minus 3.
Mhm.
I mean, like,
Yeah, be careful with these ones. A lot of people use 5s and 1s or 6s and 1s. We have to have the correct numbers here. This is -3, -2. So y minus 3, y minus 2. We okay with that one? That means that y equals 3 and y equals 2. Y equals 3 and y equals 2. And are we going to stop right there? Well, let's look back. Our variable was in terms of x at the very beginning. What's the variable we ended with? That's not a good thing. So can we get back to x's? Well, this is like your trail of breadcrumbs. This told you what you did, right? So if we made a substitution y for e to the x, now we're going to reverse that. We're going to do a substitution e to the x for our y. Are you guys okay with that so far? I know it's just algebra, but I want to make sure you guys are good at this. So instead of y equals 3, what could I write, please?
Yeah.
And instead of y equals 2, I could have e to the x equals 2. That's excellent. Now, oh my goodness, can you solve that? If e to the x equals 2, can you solve it? How would you solve it? Yeah, which particular type of log? The natural log. That's right, the natural log. Because we want to match up our bases. So if we take a natural log on both sides, like this, ln e to the x equals ln 2. Do you guys remember, we went over it yesterday, remember what happens anytime you have ln next to an e? We could move this forward, ln of e is 1, so what's on the left-hand side of our equation?
X.
On the right-hand side? That's actually one of our solutions. So x is ln 3, natural log 3. Over here, same thing happens. We get x equals 2. That's it. I want a quick show of hands if you feel okay with that algebra. You sure? Are there any questions at all? So our ideas are, once again, if you have multiple ln's, try to combine them. Because that way when we do e on both sides, it actually works out, okay? Otherwise, it's not going to work out. Also, whenever we have some things that have potential to be quadratics, try substitution. Try to work with some of the algebra techniques that you've already learned. That'll oftentimes make it easier. Are we okay with these two? Okay, before we get on to the calculus involving exponential, well, e to the x, we got to talk about a few properties. So, make a few notes here. These are going to be important. We're going to use these a lot. It's going to be helpful for us to have a good picture of what the function e to the x actually looks like. Then these properties are going to make a lot more sense to you. Do you guys have a good picture of what e to the x looks like in your head? Do you know what it looks like?
No.
Does it look like ln? Is it a straight line? Okay. Let's start easy. If you plug in 0, how much is it going to give you?
1.
If you plug in 0, e to the 0 is
1.
Good. So we're going to cross for sure at 0, 1. Notice how he's about the number 2.7, all right? So if we plug in bigger numbers, if we plug in like 1, I'm going to get out 2.7. If I plug in 2, that's going to be 2.7 squared. If I plug in 3, 2.7 to the third power, and so on and so on. Is it going to climb or fall? Climb, and climb fast. It's an exponential. Exponentials climb fast. Over here, negatives. If I plug in -1, am I going to get a negative number?
No.
No. If I plug in any negative, am I going to get a negative number?
No.
So this thing is going to be above the x-axis all the time. Can you verify that for me? It will never cross the x-axis because it never actually equals 0. So what this thing looks like, it does cross at 0, 1. It climbs over here. It's asymptotic to the x-axis as we go to negative numbers. Have you seen that before? Yeah, it's that function. It climbs the whole time. We okay with that one? Well, if we got a picture of this, you guys see why, by the way? If we plug in negatives, such as e to the -2, really that's just 1 over e squared. It's not negative. It's just a really small number, and it gets smaller the more negative number we put in there. If we got the picture, these ones make a lot of sense. Firstly, let's talk about the domain and the range. Domain. The domain is, well, the inputs or the outputs. You guys should know that. Good. And well, what is that? Is it the inputs or the outputs? Domain always has to deal with the inputs. So, what can you plug into e to the x? Is there any restriction on it whatsoever?
No.
Then you're correct about the domain. Domain is -infinity to infinity. It says that you can plug in anything along the x-axis, you're good to go. You're always going to find an output for that. Make sense? Okay, how about the range? Is the range -infinity to infinity? What do we get out of this thing?
0 to positive.
Do we actually get out 0?
No.
Okay, so how can I show that with my range?
With the parentheses.
Do you remember doing the interval notation when, yeah, we don't get out any negatives. Firstly, verify that for me. Can you see that? We don't get out any negatives, so that's not in our range. We don't get out 0, but we get things that are very close to 0. It's almost like that limit idea that you have. We approach it, we never get to it. So we use the parentheses to signify that. How high do we go? Yeah. Can you guys see the domain and the range on the picture? Does it make sense to you? All right. Oh yeah, next up. Continuity. Where is it continuous? For continuity, we always use the domain idea of that. We say the x values or the input values for which this thing is continuous. So what's the interval of continuity for our function? Is it continuous everywhere is what I'm asking you. Is it continuous everywhere?
Yes.
So it's continuous on its entire domain. What's also interesting, let's talk about concavity. Does this function ever change concavity? Ever. Remember what concavity is? Concavity is the way the shape is curved. That doesn't make sense. The curve is shaped. So it's either increasing in an increasing fashion or increasing in a decreasing fashion. This happens to be concave up, increasing in an increasing fashion. So here we have concave up also for the entire domain, which is interesting. It's always holding water. I think that you learned that in Calculus 1. If it can hold water, then it's concave up. If it's an umbrella, then it's concave down. Well, this thing's always concave up, the entire curve. Also, we talked about one more thing, and we'll give you some examples here. Let's talk about the limit as x approaches positive infinity and the limit as x approaches negative infinity. So how much is the limit of e to the x as x approaches positive infinity? Do you remember what that means? It means as we go this way, where's our function going? Is it going up, down, or level? Up, forever and ever and ever. So what's the limit of e to the x as x approaches positive infinity? What is it? Yeah, it's going way up there. It's going to infinity. How about the other way? What if we go all the way to the left? So as x approaches negative infinity, what is our function doing? What's our function's value as x gets further and further away negative? What's it going to?
Zero.
It's going to 0, that's right. I'm going to give you two more. This really isn't in exponentials, but it's going to help you because sometimes we deal with the limit as far as ln goes as well, so I want to give this to you as well. If you remember this, I hope that you do, the function e to the x and the function ln x are inverses. Do you remember that? So ln x looks like this graph. I think I drew it for you earlier where it looks like that. Do you remember that? That would be ln x. So e to the x and ln x. If I go to positive infinity for the ln x function, what's the limit as x approaches positive infinity of ln x?
Positive.
It's still infinity. It's climbing slower, but it's still climbing. You guys okay with that one? Are you sure? Okay. How about the limit should I make this limit go to negative infinity for ln x?
No.
Is that even relevant?
No.
Can I plug in negatives at all to my ln function? I don't know. Look at this, the dotted line. Are there any negatives over here? Does the dotted graph exist over here? Then that would make no sense. What number do I want to see this approach? 0. Can I do this? Would that make sense?
No, it has to be from the positive side.
Very good. When we're talking about limits, remember that for a limit to exist, it must exist in both directions. So if I have this, it's actually inaccurate. This says that this would be from both ways, and that's not the case. It doesn't even exist over here. So we'd say from the right-hand side, what's happening here. Are you guys okay with that notation? This says find the limit of ln x, no problem, as x approaches 0. Okay, I know where that's at. From not both sides, it doesn't even exist over here, but from the right-hand side. So what's happening to my function ln x as I'm going this way, getting closer and closer and closer to 0? What's the value of my function approaching? It's not 0. It's going down, 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 down. Negative infinity. That's a horrible negative infinity. Gosh darn it. There we go. Would you like a couple examples on how to use this in some limits? Because you're going to have to. Do you want to see some? Firstly, do these properties make sense now that you have a good picture of what the ln and what the e to the x look like? Good. Let's do some examples and actually apply it.
The University of Arizona Online brings a top-ranked education to you. Choose from 150 plus programs, learn from the same faculty, and earn the same degree as on-campus students. Apply today and make your tomorrow amazing.
With the Wells Fargo Active Cash Credit Card, earn unlimited 2% cash back on purchases you want,
Ow.
like dance lessons.
Ow, ow, ow.
And on what you need, like memory foam inserts. That's real life ready. Visit wellsfargo.com/activecash. Terms apply.
Real quick examples. Oops. Okay, let's take a look at that one. So limit x approaches negative infinity of e to the negative x minus 2e to the 2x over, my goodness, that looks like a bunch of junk. You know what? It's really hard to think about what's going on when you have all those negative exponents floating around, isn't it? Go, wait a second, this is e to the negative but that's negative infinity. So e to the, that would really be infinity. Well, that's infinity already. So if you think about this, this would be infinity minus, well, that's going to be 0, but this is going to be infinity over infinity. Can we do limits if you have infinity over infinity? Does this, let's see if you know. True, false? Infinity over infinity, it's what? No, that's not true. We can't do that. So we got to work around this somehow. And I believe in your 4A class, what your teacher should have told you is that you're going to look at your denominator and you're going to divide by part of your denominator. Typically, it's the largest exponent. Here, because we're going to negative infinity, it's going to really suit us to get rid of this e to the negative 2x, because what that's giving us, this is giving us an infinity here. Does that make sense to you? That's the problem. So what I want to do, I want to show you a couple tricks on how you get around these ideas. One thing I'm going to do here, I'm going to take this, by the way, you typically always in your, this isn't really a rational function, but when you have these fractions, you'll typically divide by something down here, not up here. You'll usually look here, okay? Otherwise, you can, if you divide by the wrong thing, you can get a 0 on the denominator, which of course we can't have that. So you typically divide by some term down here. I'm going to divide everything by e to the negative 2x. Let's see if we can do this together, okay? I'm still going to have a limit. Negative infinity. Remember, when we divide, we're dividing every single one of these terms. So let's do this. How much is e to the negative x divided by e to the negative 2x? How much is e to the negative x divided by e to the negative 2x? Recall that when we divide common bases which have exponents. This is what we're doing here, folks. Are you guys okay with that idea? What do you do with your exponents? You add or subtract? Subtract. So negative x minus negative 2x, how much is that? So that's e to the x. Are you okay with the e to the x? Negative x minus negative 2x, we're basically adding negative x plus 2x. Minus. How about this one? Let's do that one. We'll change this around. Here we have 2e to the 2x over e to the negative 2x. Remember that we're dividing each term by this. So each term by this. What's our answer going to be? So we're still going to have the 2 though, right? Again, what do you do when you have exponents over exponents? You add or subtract? 2 minus negative 2. That's e to the how much? Are you okay with these? I'm not getting a whole lot of participation. Do you see where these are coming from? Are you sure? So 2e to the 4. Okay, that's cool. Now, this one should be easy. What happens when you take something and you divide it by itself? How much is that? I love that one. This is 1. And lastly, if we have 3e to the 2x, what's that going to give us?
E to the 4x.
Okay. Well, that makes it at least a little bit more manageable. Let's see what happens here. Oh, you know what? We actually have some properties for that. We have some limits. We should know what that means. Let's think about this for a second. What happens when I go e to the negative infinity? What is that? What's the limit as x approaches negative infinity of e to the x? It should be right down there. How much is that? So this thing is 0. How about e to 4x? Well, think about this. What's 4 times negative infinity? If you were allowed to plug that in, what would that be? It'd still be negative infinity. Okay, so this is still e to the negative infinity. How much is that?
0.
Still 0. Are you guys okay with that one? So this is still 0. 1? How much is 1?
1.
That's nice. I like that. That's what we're trying to get. That's why we divided, so we can get this constant in there somewhere. How much is, oh, look at this. We have basically the same thing. How much is e to the 4x again as x approaches negative infinity? It's still 0. So practically, we have 0 minus 0 over 1 plus 0. I messed up. 0 minus 0 over 1 plus 0. That's 0 over 1. Is it okay to have 0 over 1? Would it be okay to have 1 over 0?
No.
Okay, so that's why we divide by the largest power in the denominator, not the numerator. What's that give us?
0.
This limit is 0. If you know anything about limits, what this basically says to you is that you, for this function, you're going to have a horizontal asymptote to the left at y equals 0. That's what that's doing. Saying it looks practically like this. Show of hands if you feel okay with that idea. All right, let's talk about one more. There's not going to be a whole lot of algebraic work in this next one, but I want you to think through what's going on, okay? So, second example. Okay, these things can really make you crazy, all right? They really can. But stick with it. Follow what the properties are telling you and change little pieces to start with. So I want to start with, we're not going to do anything in this problem, okay? We're just going to think about it. We're going to think what each piece means. Let's start here. Don't even worry about the 1 over. Just tell me, what is ln x? What's the limit of ln x as x approaches 0 from the right? We had that down here, didn't we? So we had 0 from the right and negative. So this piece right here, that little piece, the ln x, is going to negative infinity. Do you guys follow me what I'm talking about? How much is 1 over, remember, this is negative infinity. How much is 1 over something that's going to negative infinity?
Small.
What do you think?
Small 0. Going to 0.
How much is 1 over negative 1, whatever this is?
Really close to 0.
It's really close to 0. Yeah, it's negative, but it's really, really close to 0. Does that make sense? So if this is negative infinity, how much is this?
0.
It's 0. Does that make sense to you? I know it's negative, but it's a really small negative number. Wow.
Infinitely.
How would you say that? Really small? Absolute value-wise, it's a really small number.
Infinitely small.
Yeah, infinitesimally small. So this little thing right here, did I blow your minds like mine grenade? Or are you guys with me? Let's start over, because I'm getting some blank looks like you're going, what? So today's lesson is not that far back, just joking. But right here, do you understand that this is negative infinity? If you divide by positive infinity or negative infinity, what do you get? Either way. So this part is really tending to 0. Are you clear? Okay. How about e to the negative x, where x is getting really close to 0? How much is this little piece going to go to?
1.
Just the negative x. How much is that? Plug in 0. How much do you get?
1.
Okay, so e to the negative x, this piece is going to be 1. That's right. Because when we get really close to 0, e to the 0 is 1. So we're going to have that. But if you look back at e to the x, when you get close to 0, when x gets close to 0, how much is our function at?
1.
So e to the negative x would be, even still, because we're doing 0, we've got 1 there. So this is going to give us 1. Show of hands feel okay with that 1. Okay, fantastic. So we know that our, let's talk about this now. On the numerator, we have e to the 0. Everybody, how much is e to the 0?
1.
Good. Over 2. Does 2 change?
No.
Plus, we have cosine pi. Cosine pi. We should know cosine pi. How much is it? Negative 1, that's right. 2 plus negative 1. So all said and done, we've got 1 over 2 plus negative 1. How much is our answer? Yeah, that's it. that's how you think about these things. Work little pieces. If you get infinity over infinity, like we would have here, you got to do something else. So start dividing by either the largest or the smallest power in the denominator if it's negative. So check that out. If you can think through the little pieces and if you get something like this, 1 over a number, that's fantastic. 1 over a number that's not 0, that's fantastic. Just work on the little pieces. It's going to take some thinking, okay? This is not a super, super easy concept. You really have to think about what's going on with each of these little pieces. Have I explained this well enough for you guys to understand it? Show of hands if I have, if you're okay with it. All right. Now, are you finally ready to do some calculus with these exponentials? So far, what you should know in this class is this. You should know how to find derivatives of natural logarithm and involving natural logarithm. That's what you should know. Do you guys feel comfortable with that one? That was your first homework. We just talked about how to do inverses because then we could get to exponentials. Inverses of logarithms are exponentials. Well, we've got to talk about how to find derivatives and integrals of exponentials now. And that's what we're going to do literally right now. And it's going to be so exciting. You're going to like this one. I really think you're going to. I like this one. This is cool. Okay, so let's talk about derivatives first. And we'll go right to it. How in the world do we find the derivative of e to the x? How in the world are we going to do that? Well, I'll tell you, this formula, it's actually pretty complicated. So if we want to do the derivative of e to the x, here's what you do. You ready for it? It's super complicated. So I want you to get a tattoo, just like tattoo it on your arm or something. So here you go. The derivative of e to the x is e to the x. Super hard. Yeah. Awesome, right? I love this one. You don't do anything with it. It's really weird. It's bizarre. What? Seriously? Did you guys know that one already? Those of you who had calculus 2 before you do. But if you didn't, then that's actually the derivative. If you do the derivative of e to the x, you get e to the x. Do you want a proof for that one? Yes. Super easy proof. It's like a really beautifully easy proof. So here it is. Let's start off with the function itself. Quick proof. Y equals e to the x. Okay, there's our function. Well, naturally, we don't know any formulas for how to find the derivative of e to the x, so we're going to kind of invent one right now. The way that you invent a formula is to do something else that you know works. So here, I'm going to do logarithmic differentiation. Logarithmic differentiation, which you did in your first homework, said, hey, if you don't know what to do or you want to make things easier, why don't you try taking ln on both sides? Oh, look at this. This is pretty cool. Here I've got ln y. Here, oh, what's this? It's x, because ln of e to the x is x. We okay with that one? Yes, no? Well, this is pretty awesome. Now with logarithmic differentiation, you knew that you do implicit. So with implicit, the derivative of ln y, treating y as a function of x, is 1 over y times times dy dx. Equals, we'd have to take the derivative here as well. What's the derivative of x? Do you remember with logarithmic differentiation? Are you guys okay with that, by the way? We took a derivative, d dx here. We did d dx here. We got 1. We got 1 over y, because that is the derivative of ln. Derivative of ln y would be 1 over y, but since it's a function of x, you need chain rule, hence the dy dx. After that, what do we do? Sure, we're trying to solve for the derivative. So if I multiply both sides, I get dy dx equals y. And if we can, we should change that back to the original function. So how much was the original function? Let's look back over there. Y equals. Yay! I love math. So what that says is the derivative of e to the x is actually e to the x. It's pretty cool. Now, we can extend this concept just a little bit with the chain rule. Chain rule happens in practically everything that we do if you don't just have one of these basic derivatives. So if we want to extend this, then we say, suppose you're taking a derivative of e to some function of x. Listen carefully, please, so you get this down the first time. If you want to take the derivative of e to some function of x, it works exactly the same way. You leave the original alone, and then you multiply by the derivative of the inside. Just like the ln derivative, remember the 1 for ln of whatever you had? You put 1 over the function times derivative of the function. Do you remember that? Here you're just going to do the function times the derivative of the function. If you like the f prime notation better, you can write it a little bit differently. Or if you want to see it with u's, if you do the derivative of e to the u, I think this is how a lot of books do it, you would have, what would you have? Yeah, you'd have the e to the u again, and then you'd have du dx. It says the function itself times the derivative of the inside, basically just the exponent part. Tell you what, I'd like to practice a few of these things just to get our brains around this. But I think you'll find that they're fairly straightforward. You obviously need to know what the chain rule is. You need to know what the product rule is. You need to know all what your trigonometric functions are as far as derivatives go. But if you know those things, this is just one more little piece of the puzzle for calculus. So let's try a couple examples, maybe 2 or 3. Okay, pretty straightforward question. Do we have chain rule or not here? What do you think?
Yes.
Unless it looks exactly like this, then yeah, you get a chain rule. So unless it looks exactly like something on your differentiation table, yeah, chain rule for sure. So here we got chain rule. Tell me the first thing that I would write. What would I write first? E to the... When we're taking derivatives of these exponentials, you don't change the function at first. The derivative of e to the x is e to the x. So the derivative of e to the negative x cubed is e to the negative x cubed. But this acts like your u, so do not forget to do what next? Chain rule, that's right. The derivative of... Can you guys do the derivative of negative x cubed? Yeah, that's a piece of cake. So we have e to the negative x cubed times, what did you say it was?
Negative 3x squared.
It's typically appropriate to write this part first. So we'd have negative 3x squared e to the negative x cubed. Okay, I want a quick show of hands if you feel okay with that one. Good. Do you guys see how this is just one more thing that we have? It's still a chain rule, but it's just one more rule that we have for derivatives. E to the x, derivative of that is e to the x. Let's do that one. It's often helpful to think through what rules you're going to need before you actually start on your derivative. So let's think about this one, x squared e to the negative 2x. What's the first thing that you should be thinking about in this problem? What do you think? Yeah, immediately we see, well, the thing that holds these together is a product. So we're going to need the product rule. Why don't you guys go ahead and write the product rule. I'm going to write it up on the board, but I want you to practice on your own right now. Let's check your work and my work. Do you guys have roughly the same thing? These, of course, can be reversed. Did you take the derivative of the first one times the second at some place, and the derivative of the second one times the first at some place? Fantastic. Okay, now you can help me out with it. Derivative of x squared, what is that? 2x. So we get 2x. Do we change this one right now? E to the negative 2x. Perfect. Plus. Do we do a derivative of this one? No, this is just x squared. Can you do a derivative of e to the negative 2x? Let's see if you got it right. This should be, well, that's a chain rule within our product rule. Here was product rule. Where am I? Product rule here. That's a chain rule inside of it. So we'll have our x squared. We'll have our e to the negative 2x. Notice we do not change that function at all the first time. It's just e to the negative 2x times the derivative of negative 2x. If you find yourself being off by constants, by signs a lot, like, man, where is that coming from? You're probably missing the chain rule. Don't forget about the chain rule in these things. It is huge. What is that derivative anyway?
Negative 2.
So 2x e to the negative 2x. This would be minus 2x squared e to the negative 2x. If you got that, did you get that? So we did it right? Do you see where the negative 2 is coming from? So this is our negative 2. We got x squared, we got e to the negative 2x. Tell me one more thing that we could do here. What can you do? Say it again. Combine, no, because we don't have any like terms.
Take out factor out.
We can factor for sure. We can factor out a 2. We can factor out an x. We can factor out an e to the negative 2x. This happens a lot with your exponentials because you get this repeating term over and over and over again, because every time you take a derivative of e, you get it back. So we get these factorizations a lot where we factor out the e's. So we get a 2, we get an x, we get an e to the negative 2x, and if we factor that, this becomes 1 minus x. Okay, I want to show if hands feel okay with that one. You ready to try one that's a little bit more tricky? Yes, no? Okay, a little more tricky. I'm going to have you do most of the work on this. I'll help you with the first step. So I would like to take the derivative of y equals ln e to the square root of x plus e to the negative square root of x. And you're going what? Seriously? Yeah, let's do it. So I want to do the derivative of this nasty thing. Let's talk about the first step together. What's the first thing that we're going to want to conquer here? Are we going to start taking derivatives of these guys right now? What are we going to start taking derivatives of right now? Very good. Do you know how to take the derivative of ln? So tell me the first thing I have when I take the derivative of this thing. Oh, I hope that you know. Derivative of ln says you do what? 1
Over the original.
over...
The inside
Good,
term.
not this, right? But just the inside. So e to the square root of x plus e to the negative square root of x. Quick head nod if you're okay with that so far. Okay, good. Are we done right now?
No.
No, unfortunately not. That'd be awesome if we were. But what do we have to do? Change chain rule. All the time, chain rule. So what we're going to do is take the derivative of... What are we going to take the derivative of? This part, yeah, that's right. E to the square root of x plus e to the negative square root of x. Okay, I want to get you started off on this one. What's the first thing you're going to have to do in order to take the derivative of these pieces? Natural log? No, not natural log, because we're taking derivatives here. We should know the derivative. But I want you to change this a little bit before you start taking derivatives of these pieces. Restate it, he said. How do you restate it? What do square roots become? Okay, so off to the side over here. So I'm going to do a little sidebar for just this piece. We're going to find the derivative of e to the 1/2 power of x plus e to the negative x to the 1/2. We okay with that? I want you to do these derivatives. Use your chain rules here and do both derivatives. Notice it's not like a product rule, it's nothing hard. Take the derivative of this piece, take the derivative of this piece. Did you get them?
Hope so.
I hope so too. Let's see if you got them. So first thing I would do this one, I do the chain rule on it. So the chain rule says that I leave it alone, I multiply by the derivative of whatever that function is of x. So x to the 1/2. Show of hands if you made it at least that far. I want at least that because you recognize the chain rule. Did you recognize the chain rule? Yes. Yeah. Okay, so plus, I leave it alone. I leave it alone, so chain rule says, leave it alone, multiply by derivative of your function of x, your exponent. Did you make it that far? Okay, these things are not so bad. So we have e to the x to the x to the 1/2 times, do you know, how to take those derivatives, don't you? This is a 1/2 x to the negative 1/2. This is a negative 1/2 x to the negative 1/2. All we gotta do, let's make this into one fraction because right now it looks really nasty. What I want to know is, did you make it this far on your own? How many people did? That's good. If you didn't, does this make sense to you? Hello, yes, no, what do you think?
Yes.
This is chain rule, right? Alone, derivative inside, 1/2 x to the negative 1/2. Alone, derivative of the inside, negative 1/2, because you get the negative, x to the negative 1/2. So far, so good? Okay. Well, if you look at these are both negative exponents. We got a couple terms here, but we can write e to the x to the 1/2 over 2 square root x. Let's verify that for me. 2's on the denominator. X to the negative 1/2 is on the denominator. The 1/2 becomes a square root. So far, so good? Okay. That changes this to a e to the negative x to the 1/2 over, same thing happens here. We've got a square root of x on the denominator. Yes, no? Okay. Lastly, do we have a common denominator?
Yes.
That's great. We can make one fraction out of it. So this negative made that to a minus. This is our 2. This is our square root of x right down there in the denominator. Now we're going to combine these. Tell me what's on our denominator, please. On the numerator, do some fancy pants math and change it back to square roots. So we got e to the square root of x. E to the square root of x. You okay with that one? Minus e
The negative square root of x.
That's right. E to the negative square root of x. Okay, we're almost done. I want to know if you're still with me. Are you still with me? Okay, almost done. What we're going to do now is we took this piece and did like a little side trip over here. So we're going to take this piece times whatever we ended with. So yeah, don't forget about that, right? So 1 over nasty stuff times even more nasty stuff. Equals the best nasty stuff, our answer. So here's what we got. Here's our derivative. This is via the chain rule right here. We had the original, this is via the ln, the derivative ln. So now we're going to put together, what we end with is e to the square root of x minus e to the negative square root of x all over 2 square root x e to the square root x plus e to the negative square root x. It looks bad, but that's our answer. Do you see where all the pieces are coming from? We get our 2 square root x right there. We get this part here. We get this coming from there. Can I simplify anything here and here? Can I simplify this?
Can't you factor out like an e to the negative 1/2 from both the top and bottom? Or e to the x to the 1/2?
Yeah, you could. You could probably do that. It's not going to make it look a whole lot better, but you could do that. I'm talking about, can I simplify this right now? If you wanted to factor, Michael, you could do that, factor a little bit out. But for right here, that's what I'm talking about. Show if you feel okay with that one. Okay, before we go, I want to talk, we're not going to do these, but I want to talk through them, okay? I want to see if you can understand the main concept behind each of these, starting with this one, with that one. What would you do for, what would your first piece that you would write be there?
X on X.
Ooh, that'd be,
Okay, so the first piece would be leave this thing alone. Do you see that? And then you'd have the derivative of, what would you do for this? That's a product rule, that's right. So you have this piece and then times a derivative that involves a product rule. Are you with me on that one? Okay, this one, what? Oh, this should be an easy one for us. What's our first step here?
change.
5 goes down. Do I change the inside?
No.
This becomes a times the derivative of this junk, and you're going to have a couple chain rules in there. Do you guys see the chain rules? So you're going to have a 2, you're going to have a -3, and they'll change that sign. Here, oh, this is a good one. This is a nasty one. What's the first thing?
Chain rule? No, product.
Product rule here. So product rule, we'd have derivative of the first times the second, plus the first times the derivative of the second. If you want, let's see if I can do this real quick. This will be negative e to the negative x tan e to the x, plus this will be e to the negative x secant squared e to the x times e to the x. And I believe those go away, because you'd add exponents, negative x plus x gives you 0, e to the 0 would be 1. I think that's your answer. I'll double check that and make sure that it's right. But does today make sense? Did today make sense for you? All right, so we're going to continue. We talked about how to do derivatives of e to the x, and we've done a lot of them. Now we're going to start talking about how to do integrals involving e to the x and what we can do with that. Now, if you remember from last time, what is the derivative of e to the x? Yeah, that was like the easiest one ever. Well, if that's the case, if the derivative of e to the x is e to the x, then the integral of e to the x is what?
e to the x plus d.
Yeah, it's e to the x. If the derivative is e to the x, the integral of e to the x is e to the x. And of course, yeah, we do have to have the plus c. Here's what that means. When we see integral of e to the x, it's super easy. You just put e to the x and you are done. The integral of e to the x is e to the x plus c. Now, of course, when we do this, we're going to have a lot of chances to do substitution. So we're going to have a lot of cases where it's not simply e to the x, it's like e to the 3x, or e to the x squared, x e to the x squared, something like that, where we can do a lot of substitutions. So in this section, you're going to have a lot of substitutions to do. So we're going to practice a few right now to see if we can get the hang of it. Are you ready?
Yeah.
Okay, we'll start real simple. What I've been telling you is that unless your integral fits perfectly into your integration table, which this is now one more integral that we can do, unless it fits perfectly, you're probably going to do some sort of a substitution for right now. Later on, we'll have integration by parts, or we'll have trigonometric substitutions, things like that. But for right now, all we know how to do is if it fits perfect, you do it. If it doesn't fit perfect, you manipulate it somehow. And one way we can manipulate it is with a substitution. Can we do a substitution here? What do you think? Substitutions are typically the inside of functions, so in this case it would be the exponent, and the derivative has to be somewhere in the integral, disregarding the constants. So, will a substitution work?
Yeah.
Let's try one. What would you pick for a substitution? Notice, we're not going to pick e to the 2x because when you take the derivative of e, it pops back up again. Does that make sense? So you'd have to have another e to the 2x in there to simplify that. We don't have that. So if we pick u equals, let's just try the 2x. What's the derivative of 2x?
2.
2 dx, or du over 2 equals dx. Okay, tell me how this changes. Instead of e to the 2x, I'm going to have e to the... Perfect. Instead of dx, I'm going to have du over 2. What can I do with that 2?
Move it out.
And what's it become?
1/2.
So then this becomes... Well, let's look at it. Did it work? Did we get rid of all the x's and have only u's left? Are you guys awake today? Did we get rid of all the x's and have only u's left?
Yes. Wait, how'd that turn?
It was magic. Don't worry. I'm changing that. Magic math. How about that one? Better? Our u matches our u, so we know that we're correct. Also, did we change this into something in our integration table? Can we do that now?
Yeah.
That's the idea of the substitution. So now that we do this, we leave the 1/2 alone. We get what? We get e to the u. The integral of e to the u is nice. And then there's one more thing. We're going to deal with the plus c in just a bit. There's one more thing I want to do here. Very good. If you start with x's, you better give me x's here. So if we start with x, we need this in terms of x. So we can do 1/2 e to the 2x. Then we put our plus c. Okay, I want to see if you're okay with that. Are you guys okay with that?
Yeah.
It's the simplest one that I can think of. We just do a substitution. Substitution, just a constant, no problem. Integral of e to the u is e to the u. Question?
Is it always gonna work like that, where you theoretically just pull the 2 and take the
If that's
up front?
if
and
that's
make it
just like a
1/2
3x,
Without, yeah, would that turn
absolutely.
into 1/3?
This is going to be a 1/3. If that's a 7x, it'll be 1/7. Now, of course, you're not going to get them that easy, all right? So if that's the case, sure, by all means, that's exactly the thing, because we'd have to do a substitution anyway. Most of the ones we're going to deal with are probably stuff that looks like this. This one, granted, is probably not so easy to do in your head. It doesn't follow this pattern exactly, so we're not going to be able to do that really easy. But the idea is the same. The idea is try to make this fit your integration table. Does this fit our integration table the way it is right now? No. Not even close. So we're going to have to manipulate. We're going to have to find some substitution. Let's think about the substitution right now. Okay, think this through. Should I pick this entire e to the 2 over x as my substitution?
No.
No, because I'm going to get that back again. Remember the derivative? You always get the e to the function back again. So we get this e to the 2 over x back again. I don't see that anywhere. So it's not going to simplify. That would be a problem. Are you guys with me on that? Okay. Is that a good substitution? The x squared. The derivative of this is 2x. Do you see a 2x anywhere? Also, even if that was there, would it possibly get rid of this?
No.
And that would be a problem. I'd have u's and x's. You can't have that. So what's the only other alternative? If we can't pick the whole thing here, we can't pick this thing, what am I going to pick?
2 over x.
Yeah, it's usually the inside of something. So let's pick the u equal to 2 over x. Now, I don't like seeing the 2 over the x, so let's change that. Instead of 2 over x, we can write that as
2x
2...
negative 1x. And
Good. We okay with that one so far? Our next step, substitution. Come on, quickly. The next step is to do what?
derivative.
So du equals, how we take derivatives, bring it down, so that's negative 2, x to the
Second. Negative second.
negative 2 dx. Very good. You guys okay with this so far?
Yeah.
Now, if we do a little bit of manipulation, you're going to see a couple nice things. Firstly, that's a negative exponent, which we typically don't like to have. So if we have du, we can set that equal to negative 2 over x squared dx. Look back at your integral. Do you see that this thing's going to work?
Yeah.
There's an x squared, here's an x squared dx. Now, I do things a little bit differently. I like to solve for dx. That's how I was taught. So if I multiply both sides by x squared, I get x squared du. If I divide by negative 2, it's over negative 2 equals dx. Let's see if that works. I know we're still going to have an integral. Am I still going to have e to the 2 over x?
No.
Am I still going to have e?
Yes.
Absolutely. I haven't substituted for that, so I have an e. What does the 2 over x change to?
U.
That's our u. Is it still going to be over x squared? Well, that depends on how you do your integral. If you like to substitute this part right here for your du, then no. If you do it like I just have done it, I'll switch back and forth to give you both aspects of this. If you do it like I do it, you'll have an x squared here, and instead of dx, you'll now have x squared du over -2. Does that make sense to you?
Yeah.
Instead of dx, I now have this piece for dx. So
Okay.
instead of dx, I have this. In my case, this is the way I like to do it because I can see stuff cross out. I like to make sure my constants are all there. That's just personally my preference. You can do it a different way if you'd like to. Do my x squareds simplify.
Yes.
Fantastic. As soon as you see that, you go, oh, that's so nice. I only have u's. It's a du integral, so we're good to go. Tell me something I can do with this -2.
Put it outside.
So I'm going to have -1/2 integral e to the u du. Okay, I'm going to do the integral of e to the u.
Yes.
Yeah, that's easy. What's the integral of e to the u? So we're going to have -1/2 e to the u
Let's see.
plus c for sure. There's one thing I'm going to do before I put my plus c so I know that I'm not done. I'm going to re-substitute in for that u. So how much is our u?
2 over x.
So we have -1/2 e to the 2 over x plus c. That's the whole idea. So if you feel okay with the whole idea. How can you check your work?
Go backwards.
Do the derivative.
What do you mean go backwards? Be more specific. Take the derivative. Do the derivative. If you wanted to do the derivative, you certainly could do it. Let's do that one. Okay, well, if you had a derivative of this piece is going to come back, isn't it? So derivative of this. Chain rule says go ahead at 2x to the -1 and bring down the -1. The negatives would go away. The 2's would go away. This would be x to the -2. That would be over x squared. So we know that we're right on this one. Show of hands feel okay with that example. It's a little more complicated, right? But can you do it? Just a substitution. Try these substitutions. You're going to have a lot of them. You guys want a couple more? Is this helping you at all?
Yeah,
that's
I'll put those.
Okay, let's think hard about this one. Firstly, does this fit our integration table exactly the way it is?
No.
No, it's not even close. Oh, here's a good question for you guys who love algebra so much. Can I split up this fraction?
No, you can't.
No, you can't split up denominators. You can split up numerators, but not denominators. So we can't split this. So we're gonna have to attack it directly. Now, the only way we can attack this thing is with a substitution. If it doesn't fit our integration model, we need to substitute. Let's pick out a good substitution for this one. Would a good substitution be this e to the -x?
No.
If I pick this one, the derivative is negative e to the -x, but it won't cross this one out because that's connected with our plus. Does that make sense?
Yeah.
Okay, how about just this e to the -x? Would I want to pick that one?
No.
Well, same basic idea. This one would get rid of this one, but, well, what about the 1?
Yeah, still be.
So let's go ahead and that actually might work a little bit, but to make things a little bit easier for us, what are we going to take? Let's take the whole thing. That way we have a u here. We know what the integral of that's already going to be, so that's nice. We don't have to do a double substitution, just a single one. If you picked this, you'd have to substitute again later, and we want to create as little substitution, as few substitutions as possible. So if we take u equals 1 plus e to the -x, and we take our derivative. Hey, everybody, what's our derivative of 1?
0.
That's kind of nice. That's why we picked it here, so that whole thing goes away. We don't have to worry about 1 plus u, and then do another substitution to get ln. Now we have just u here. That's what we're going to end up with. How about the derivative of e to the -x? Let's do that. Why don't you do that one on your own, see if you can do that. So write it out real quick. So this, of course, is 0. We all know that one. Find the derivative of that. Remember, with derivatives of e to the x, or e to a function of x, we leave the function alone. So the derivative is e to the -x But I'll tell you something, if you're off by constants a lot, or you're off by, man, I don't know where this x is coming from, you're probably forgetting the chain rule here. So what you need to make sure you do is that with all these e's, with all these e functions, don't forget the chain rule. So the chain rule says, sure, I'm going to keep the e to the negative x, but I'm going to multiply by the derivative of negative x. What's the derivative of negative x?
Negative 1.
So du actually equals negative e to the negative x dx. Is it going to work?
Yeah.
Do you see it? Do you see it in the integral? Check this out. Some of you guys were taught to do integrals this way. Do you see the e to the x dx up here?
Yep.
You can do that substitution. Pull the negative over here. This is going to equal negative du. If you know how to do integrals that way, do it that way. Don't care. If you learn how to do them like I did,
Solve for dx.
you can solve for it. And now we can do our substitution. So why don't you tell me, just left side people, you guys over here, tell me please what is on the top of my integral. It depends on the way you do it. For the way I'm doing it, what's on the top of my integral right now?
E to the negative x.
How about on the bottom of my integral, what am I going to have there? You can say it out loud.
U.
And here I'm going to have du over negative e to the negative x. I'm substituting, instead of dx, I now have du over negative e to the x. So instead of dx, I'm doing my substitution. This stays, this becomes a u, and now we get to cross those out. We can simplify. E to the negative x is gone. Tell me one thing I'm going to do before I start my integral.
Take this.
Yeah, let's do that. So this becomes the negative integral of, what's inside there?
1 over u du.
Oh, how about that?
Look at that.
Can you do the integral of 1 over u?
You can.
How much is the integral of 1 over u?
ln absolute value u.
Perfect. I like the absolute value. So negative ln absolute value of u. I'm going to put a plus c after I make sure that I substitute back in there. I don't want to put a plus c and then go, oh, I'm done. You don't want to do that, okay? If you want to put the plus c now, you can. But I like to do it later, just so I don't forget that this was in terms of x. I don't want to leave it in terms of u. That's not the idea here. So instead of negative ln absolute value u, we put negative ln absolute value of, what's in there?
1 plus e to the negative x plus c.
Now we put a plus c. Please keep that absolute value unless you can get rid of it. Now I want you to look at that real careful. 1 plus e to the negative x. Can this ever be negative?
No.
Okay, so you can choose to leave it if you want to in my class, but in the back of the book, they're probably not going to have the absolute value. They're probably going to have this. Negative ln 1 plus e to the negative x, because those absolute values are irrelevant in this case. It can't be negative. It doesn't matter. Plus c. Did that one make sense to you? Okay. Yeah. Tell you what, let's try, we'll do one more together. We'll talk about one more, and then we're pretty much done with this section. We'll move on. Are these easy, medium, or hard? Are they more understandable now? Are you starting to get the idea here? Man, I bet you guys are going to be pros at substitution after this. I know you learned it in your last class, but we use it so often, it's just incredible. We use it all the time until we get to chapter 7. Okay. Integral e to the negative x secant e to the, oh my goodness, that's nasty enough for you in the morning, isn't it? Let's try to find this out. Is this something that fits in our integration table the way it is right now? No, not even close.
Oh, no.
I see a secant. That's kind of cool because we now know the integral of secant. That's fine, and we know the integral of e to the negative x, but not all of it together. If you forgot about this, what you can and can't do, what you can't do is just take the integral of each little piece. You can't do that when they're multiplied together. When they're added, sure, but not when they're multiplied. So we're going to have to use a substitution to try to change this into something that fits our integration table. Let's talk about a substitution. Would a substitution be good for this e to the negative x?
No.
If you picked it, you'd get it back again. But will
You
this
won't get rid of this.
cross this out? No, this is the argument of angle. You cannot cross that out, okay? The argument of secant, you can't cross that out. Would it be a good idea to take this entire thing as your substitution?
Still have.
Remember that you have to do derivatives, correct? So the derivative of secant is secant tangent. Do you see a secant tangent anywhere up here?
No.
That'd probably be a bad choice. What's the appropriate choice for our substitution here?
The e to the negative x inside the secant thing.
That one. Yeah, that's the appropriate one. If we pick this one, we just dealt with this, so I'm not going to bore you with asking you again. The derivative of e to the negative x is negative e to the negative x dx. Again, do you understand where the negative's coming from? Tell me where that comes from, please.
The chain rule.
Perfect, chain rule. Okay, so, hey, is it going to work?
Yeah.
This is this piece. We can make a substitution. If you like doing it this way, if you like doing that substitution, here's one way you can solve for it. So just a different method of showing this. Put the negative over here, so negative du, any constants over here, and the substantial portion of your substitution here. This piece is this piece. This now, these together become negative du. Do you guys see that? It's a different way to think about that. So here's an integral. If I do my substitution, tell me what's left on the inside of my integral, please. On the left-hand side, you guys. What's in here still? Secant. Very good. I like the secant. Did you say u or e to the negative x?
U.
Okay. And now, if I take my e to the negative x dx, e to the negative x dx all together becomes... Tell me what we're going to do with the negative.
Move it up to the front.
Okay, so I'm going to move up here. Man, we're almost done. Does it fit our integration table now?
Yeah.
That's the whole idea of substitution, is make it fit, make it work. I know it's going to be negative. Oh, do you remember the integral of secant? We did it a few classes
Absolute value
ago.
of secant u plus tan u.
Definitely an ln, which was kind of interesting when you think about it. Inside there should be secant u, tangent u, correct?
Plus tan.
Oh yeah, sorry, plus. Close the absolute value. Tell me one more thing, everybody, we're going to do before we end this problem.
Put your u back in.
Okay, so negative ln absolute value. Secant, what is our u anyway?
E to the negative x.
Right there, we got a breadcrumb trail. Tell us what to do. I'm going to put some parentheses there, plus tangent, e to the negative x, absolute value plus c. Sorry, that's all scrunchy. I got to fit it on the screen. So negative ln absolute value secant e to the negative x plus tangent e to the negative x and absolute value plus c. Oh my gosh, if you had that the first day of class, wouldn't you kind of be crying? Now is it hard? Is it? Can you understand it at least? It's doable. You guys can do this. If you can do a substitution, you can do this. We now know what derivative of e is. We need to make sure we have chain rules. That's going to give you a different sign out front if you forget the chain rule, okay? You need to remember that. Now, if we have substitution and we understand how to take derivatives, we're good to go. I'm going to talk about one more. We're not going to finish this problem, but I want to talk about it. You know, one of the hardest parts for students is picking the appropriate substitution. Now, of course, if you pick the wrong one, it should be apparent to you really quick, but you waste time. So let's think through what the appropriate substitution would be in this case. And maybe you can try this one later at your own convenience. Well, you tell me good or bad? This piece, good or bad? That'd be bad, because it's not going to cross out anything. This piece, good or bad? This piece.
Bad.
Good and bad. Well, it would cross out this one, and that would be
We'll get rid
u,
of that one.
but I'd still have x's right there. That would be a problem. We won't get rid of everything. Does that make sense?
Isn't that the same as that, so both of them would be U?
Yeah.
Do you know how to do a ln u over u?
No.
Me neither. So let's make a different one. Well, I can, but it's a different topic. We haven't covered that yet, okay? How about this inside? Would that be a good choice?
Sounds good to me. Yes.
If I did this one, I'm going to get e to the x back again. I'd have ln u, and I'd have an e over e to the x. This would cross out. This would not cross out.
You have to get the ln with it.
This is your appropriate choice. Your u here should be ln e to the x plus 1. And here's how I know that. If I do the ln e to the x plus 1, look what ln gives us back. Look,
Plus
look.
1.
If you take the derivative, you're going to get 1 over this. Does that make sense?
Yeah.
Here's 1 over this. And then you have a chain rule, you're going to get e to the x back again. Here's e to the x back again. If you do that u substitution, this thing works out perfectly. It's really easy. Okay, so try that later. Try looking through that, seeing that that is the correct substitution. Try that problem. Show of hands if you feel okay on the stuff we've covered so far. Any questions at all? Is it becoming easier for you, I hope?
Yeah.
Well, get used to substitutions and it will. It will become easier, I promise. Now, the next thing we're going to do is we're going to take this one step further. Instead of just doing derivatives and integrals that involve e to the x, an exponential, we're going to talk about exponentials in general, where the base is not just e, but where the base is any other number, a constant, for instance, or even another function of x. So when we start section 6.4, we're going to discuss general exponential functions and general logarithmic functions. Instead of just dealing with e to the x and ln x, we're going to have any base to the x and a logarithm of any base besides e.
Let's put this old phone back in service with the new Generate Background feature in Photoshop. First, we'll remove the background. Then click Generate.
General exponentials and logarithmic functions. You know, there's a couple things I want you to recall before we actually